Good day, G10. So for today, we are now on our third topic for the third quarter. On this video, we will be dealing with the graph of polynomial functions. On this lesson, you will understand, describe, and interpret the graphs of polynomial functions. To give you some sort of overview for the topic, this is an application of the graph of polynomial function. Polynomial functions are used to model many real-life situations. In business, the behavior of the stock market, in particular, the behavior of the Philippine stock market from 1992 to 2020 can be modeled using a polynomial function, which is described on the given figure. Our key question for this topic is, how does the graph of polynomial functions aid on interpreting the behavior of the stock market and other real-life applications? How does it facilitate in decision-making? Let us start with the nature of polynomial functions and its graph. Here are some of the important principles that must be kept in mind before graphing polynomial functions. First, a polynomial function of the nth degree cannot have more than n roots. This only means that the graph cannot intersect the x-axis more than n times. Second, the graph of any type of functions must pass the vertical line test. This means that when you draw a vertical line anywhere on the graph of the function, it will pass only once. Last, every polynomial function with real coefficient has the set of real numbers as its domain. Thus, the graph of a polynomial function is continuous. It has no gaps or breaks. At this point, we will be discussing the key points that are needed in describing and interpreting the graph of polynomial functions. Turning points. The turning point of the graph of a polynomial function is the point where the graph changes direction. That is, from a rising to a falling direction or vice versa. If p of x has n degree, then it has at most n minus 1 turning points. Considering different types of polynomial functions, the degree of the function will show the number of turning points the graph contains. Y equals x plus 4. The degree of the function is 1. Therefore, the graph does not contain any turning point. Y equals x squared plus 4. The degree of the function is 2. Therefore, the graph changes directions once. The graph goes from decreasing to increasing. As you can see on the figure, the graph is a parabola. Y equals 2x cubed minus 5x squared minus 3x plus 6. The degree of the function is 3. Therefore, the graph changes directions twice. The graph increases from left, then tends to decrease, and then increases again to the right without bound. Another key point is the intercept. Intercepts are used to determine the points where the graph intersects or touches the x and the y axis. First, the x-intercepts. Those are the value of x for which p of x equals 0. They are the real zeros of the function. A polynomial can have no x-intercept, one x-intercept, or several x-intercepts. Second, the y-intercept. That is the value of p of x if x equals 0. The graph of a polynomial function has only one y-intercept. Considering y equals x plus 4 and solving for its x-intercept, we have y equals x plus 4 and then equate x plus 4 to 0. Solving for x, we have x is equal to negative 4. Solving for the y-intercept, we have y equals x plus 4. Substituting 0 for x, we have y equals 0 plus 4. So, we have y equals 4. The function y equals x plus 4 has only one x-intercept, which is negative 4. And its y-intercept is 4. Next, we have y equals x squared plus 4. Solving for the x-intercept, we have x squared plus 4 equals 0. And x is equal to square root of negative 4. The square root of a negative number is imaginary. That's why x is equal to positive negative 2i. Solving for its y-intercept, we have y is equal to 0 squared plus 4, which will be equal to y is equal to 0 plus 4, meaning to say y is equal to 4. The function y is equal to x squared plus 4 does not have x-intercept since the computed value of x are imaginary, and its y-intercept is 4. It is reflected on the graph that the function does not intersect the x-axis, but it intersects the y-axis at y is equal to 4. Third, we have y is equal to 2x cubed minus 5x squared minus 3x plus 6. Since the given function is of third degree, to solve for the x-intercept, we will be applying the concepts in solving for the roots of the function. The factored form of the function is x minus 1 times the quantity of x minus the quantity of 3 plus minus square root of 57 over 4. Therefore, the values of x are 1, 3 plus the square root of 57 all over 4, and 3 minus the square root of 57 all over 4. Solving for the y-intercept, substitute 0 for all x on the function. Y is equal to 2 times 0 cubed minus 5 times 0 squared minus 3 times 0 plus 6. Y is equal to 6. The function y is equal to 2x cubed minus 5x squared minus 3x plus 6 have 3x intercepts since its degree is 3. For its y-intercept, the value is 4. Third key concept is the leading coefficient test. It is a test that can help determine the end behaviors of the graph of a polynomial function as x increases or decreases without bound. We can categorize the end behavior of the graph into 4 types. The first one is if the degree of the polynomial is odd and the leading coefficient is positive, then the graph falls to the left and rises to the right. Example is y is equal to 2x cubed minus 7x squared minus 7x plus 12. Its graph is shown on the right. Its degree is 3 and its leading coefficient is 2. The graph falls to the left and rises to the right. Second type is if the degree of the polynomial is odd and the leading coefficient is negative, then the graph rises to the left and falls to the right. Example is y is equal to negative x raised to 5 plus 3x raised to 4 plus x cubed minus 7x squared plus 4. The graph is shown on the right. Its leading coefficient is negative 1 and its degree is 5. Third type is if the degree of the polynomial is even and the leading coefficient is positive. Then the graph rises both to the right and to the left. Example function is y is equal to x raised to 4 minus 7x squared plus 6x. The leading coefficient is 1 and the degree of the polynomial is 4. Fourth type is if the degree of the polynomial is even and the leading coefficient is negative. Then the graph falls both to the right and to the left. Example, y is equal to negative x raised to 4 plus 2x cubed plus 13x squared minus 14x minus 24. The leading coefficient is negative and the degree of the polynomial is 4. Another thing to consider is the multiplicity of the zeros. As x increases from left to right, note that the sign of p of x changes from one side to the other side of the zeros. The table shown summarizes the effect of the multiplicity of a zero on the graph. Take note that c on the table represents the zero of the function. If the multiplicity of a zero is even, the sign of p of x does not change from one side to the other side of c. Therefore, the graph touches the x-axis at c. If the multiplicity of a zero is odd, then the sign of the polynomial changes from one side to the other side of c. Therefore, the graph crosses the x-axis at c. For example, the function y equals 2x cubed minus 7x squared minus 7x plus 12 has a factored form of y equals 2x plus 3 times the quantity of x minus 1 times the quantity of x minus 4. The zeros of the functions are negative 3 halves, 1, and 4. And each multiplicity of the zero is 1. Therefore, the graph crosses the x-axis at negative 3 halves, 1, and 4. Another function is y is equal to negative x raised to 5 plus 3x raised to 4 plus x cubed minus 7x squared plus 4. Its factored form is y is equal to the quantity of x plus 1 squared times the quantity of x minus 1 times the quantity of x minus 2 squared. The zeros of the functions are negative 1, 1, and 2. The multiplicity of each zero is 2, 1, and 2, respectively. Therefore, the graph touches the x-axis at negative 1. It crosses the x-axis at 1 and touches the x-axis at 2. At this point, we will be using all those key concepts in graphing a polynomial function. Graph the polynomial function g of x is equal to x cubed minus 6x squared plus 11x minus 6. Step 1. Determine the number of turning points. The given function is of the third degree. Therefore, it has at most 2 turning points. Step 2. Solve for the x and y intercepts, then plot the corresponding points on the Cartesian plane. Solving for x-intercepts, we have g of x equals x cubed minus 6x squared plus 11x minus 6. Equating g of x to 0, we have x cubed minus 6x squared plus 11x minus 6 equals 0. Next, we have to solve for the roots of the function using the integral root theorem. The possible roots are positive negative 1, positive negative 2, positive negative 3, and positive negative 6. Choosing one from possible integral zeros and applying synthetic division, we have the depressed equation is x squared minus 5x plus 6 equals 0. Factoring further to get the other roots or x-intercepts, we have x squared minus 5x plus 6 equals 0. The factors are x minus 3 and x minus 2. Therefore, the x-intercepts are 3 and 2. And for this function, all the x-intercepts are 1, 2, and 3. While for solving for the y-intercept, let g of x be equal to y, and then substitute 0 for all x on the given function. We will have y equals 0 cubed minus 6 times 0 squared plus 11 times 0 minus 6. Therefore, the y-intercept is negative 6. Plotting the corresponding points on the Cartesian plane, we have 1, 0, 2, 0, and 3, 0 for the x-intercepts, while for the y-intercept, we have corresponding point 0, negative 6. The leading coefficient of the function is 1, so it's positive. The degree is 3, so it's odd. So the graph falls to the left and rises to the right. Step 4. Describe the behavior of the graph with respect to each zeros of the function. The function in factored form is y equals the quantity of x minus 1 times the quantity of x minus 2 times the quantity of x minus 3. The zeros of the function are 1, 2, and 3, and its multiplicity are all 1. Therefore, the graph crosses the x-axis at 1, 2, and 3. Step 5. Estimate the location of the graph in between the intercepts. Considering the x-intercepts of the function, there will be 5 intervals on the x-axis, which are from negative infinity up to 0, from 0 to 1, from 1 to 2, from 2 to 3, and from 3 up to positive infinity. We will be picking values of x, or the test values, in between those intervals, which are 1, 1/2, 3/2, 5/2, and 4. We will then substitute those values of x on the given function, and we will come up with the value of g of x, or y, which are negative 24, negative 1.875, 0.375, and negative 0.375, and 6. And those values of g of x reflects the location of the graph on our x-axis, which are below the x-axis for the values of negative 24 and negative 1.875, while above the x-axis for 0.375, below the x-axis for negative 0.375, and above the x-axis for 6. Step 6. Roughly sketch the graph. Use the test values as value of x and g of x as values of y on sketching the graph. That is how we graph polynomial functions. Hope you understand our topic. If you have any questions, reserve that in our synchronous session. Goodbye and God bless G10.